Unless you guys don't want to go through 23. I guess that should be a question.
Yeah, let's go through 23.
Go through 23? Okay. Well, sweet. That's perfect. So I want to talk through 23. Then I've got a big list of things talking about Newton's third law today. It'll be great. We're just going to keep hammering at home because it's important. The most important, in fact, thing that you're going to learn about Newton's stuff. So it's, indeed.
Wait,
But,
did you start recording?
yeah, I did. In fact, thanks for asking. But I am going to hide that so I don't turn it off. There we go. All right. So number 23, this is the one. So remember yesterday I handed back tests and I just recorded them. I've not put them in PowerSchool, but I will do that hopefully today. Oh, I'm free so you can see it too. That's just not my party. There we go, 23, thanks. If you want to come in and make corrections, please do that. Let's say by the end of next week. Can we do that just so that we have like a time frame on it?
So it can be next week?
That's fine with me because I feel like this week is short and confusing and crazy. So let's just say by the end of next week, get those done, okay? You can do it during a free period. You can do it during AFT. You can do it. I don't usually come in early, but if you need to come in early, then we can like give them to Mrs. Hughes and you can do them in her room. I can't send the test home with you, but as long as, if you can find time, we can make it work. And I'm here after school too. All right, 23, this is one on the homework that I want to make sure. Let's see. So it says, each of these boxes is pulled by the same force to the left. All the boxes have the same mass and slide on a friction-free surface. So this should look familiar to you, right? There was one on the review and there was one on the test that were both very similar to this. So I just really want to make sure that you've seen this, it makes sense to you. This really, to me, seems like a Newton's second law question. I don't really know why it's in here, but I'm just going to take advantage of the fact that it is. So there's a force that's pulling on this box, and this one's called A. And then there's two boxes that are hooked together and a force that's pulling in. This force, it says, is the same force, right? All of them have the same force F, and this is B. And then the last one has the same force F, and it has, I think, 3 boxes. Does this look familiar to you? Yes? Are we okay here? Yeah? And this was letter 3, or letter C. And then it says part A says to rank the following from greatest to least in terms of the acceleration of the boxes. What are you gonna do?
Was this like problem 1?
I don't remember which problem it was on the test. It was one of them.
Oh, yeah.
It wasn't number 1. It was the first one on one of the pages.
Wait.
But I don't know if it was this. It was something like
I
this.
think I just.
But I want to make sure that we're thinking about it big picture so we
I
understand.
think I did it wrong. Well, I did it wrong on homework. But okay, so you use the acceleration equals F net divided by M.
Okay, hold on. Let me write that down. So acceleration equals F net divided by M. Okay.
So I think then, since the forces are all the same, the only thing you're dividing by is the mass, and since A has the least amount of mass,
Okay.
that would be the greatest acceleration.
Okay. What do you guys think? Okay.
And then B would be, so A would be greater than B, and B would be greater than C, just because A only has like 1 M, B has 2, and C has 3. So you're just dividing by more, so the number's gonna get smaller and smaller.
So if we call it 1 or 2 or 3, let's just like keep it simple, right? F net divided by 1, whatever that F is, right? For B, A is equal to F net divided by 2. And we can think of it in this part, that's exactly right, Madison. We can think about this as like one big box with a mass of 2, okay? Does it make sense that these 2 boxes in B will have the same acceleration?
Yeah, because the rope.
The rope is pulling on it, right? The rope is pulling on it. And so if this one accelerates the one on the left, then the one on the right has to accelerate the same amount, right? Are you with me there? Yeah. Yeah. So the 2 boxes in B have to accelerate the same amount. And so, yeah, I think we're good. And then the acceleration for C, why is this being so goofy again? F net over 3. So yeah, I'm thinking that A is going to accelerate the fastest. How is that feeling to people? Is that okay? Sweet. All right, then there was part B, wasn't there? Part B says the tension in the rope connected to the boxes on the right in B and C. So now I think that they just want to know, like, tell me about this rope here versus that rope there. Is that what they're talking about? Yeah. How are we going to do that? How are we going to approach that one? Question B says the tension in the ropes on the right-hand side. How are we going to do it?
Maybe we can pretend like they all, like obviously all the boxes are similar, so we can just like create a mass of our own box for this question.
Okay. So tell me a little more.
And also, and this is friction free, so I know that has a part to play with it. So, I mean,
Keep talking. You're
if there's no
doing
friction,
great.
that means that the acceleration is.
You're totally there. But can I maybe fill some words in for you? So if we're just looking at this box here, I'm just going to draw it down here. So this is the rope I care about. Here's the box. In the X direction, what forces are acting on the box? Is there friction?
Oh, no friction.
No friction. So it's just that rope, right? Yeah. So for this box, the net force is equal to just that tension force. You okay there? The only force acting in the X direction for this box is just the tension. Okay. We know the acceleration in this box is equal to, in that case, the tension divided by the mass. How are we doing? Are we okay there? You could say the same thing for the one in C. I'm just going to do this in a different color so we can kind of compare them. F net here is also FT, but we're comparing those FTs. So we'll call this FT for the orange one and FT for the pink one. How do the accelerations for the pink one and the orange one compare? Are they the same? The accelerations aren't the same. How do the masses compare? How does this mass compare to this mass? They're the same. Yep. Are the accelerations the same?
Yeah.
You just told me they weren't.
I don't know. I was confused. I don't think that. I think that they're the same.
That the accelerations are the same?
Didn't you say that earlier?
I didn't.
With the question. Wait, no, I lied. Because of the first question, the acceleration.
Yes. So the acceleration of A, you said was greater than the acceleration of B, was greater than the acceleration of C. Yeah? Yeah. So that means that this one has a greater acceleration than this one. You with me there? So this one has to have a bigger tension force. Yeah, because it has a greater acceleration. We okay?
What?
What?
Yeah, okay, no, wait. I think I
Basically, because there's a,
Why does that one have a greater acceleration?
Because you told me it did.
No.
wait, wouldn't it have the least?
Yeah.
Or you're saying the block in the back has the most acceleration?
Okay, let's back up for a second. I think I was talking too fast.
Sorry.
No. Don't need to apologize. I just want to make sure we're okay. The first question we asked was just about the acceleration of the boxes. True?
And it was A is greater than B, which is greater than C.
A is greater than both of B, which is greater than all three of C. Right? All three of C are the same. Is that okay? And the acceleration here is very, very small compared to this one. Right? It's less here because there's more mass. Is that okay? So all I really care about is this is true. Is that okay? Yeah?
Yeah.
Okay. I want to know about that force, that green tension force that I highlighted. If I know the acceleration of this one is bigger than the acceleration of this one, and the mass of this one is the same as the mass of this one, what can you tell me about the force? Smaller on C. Yeah. Yeah. That's the answer. So C is smaller than B, or B is greater than C.
Okay, wait, scroll down for a second.
Is that what you wanted to see?
Yeah, I was just confused because I thought that you were saying C was greater than B, but that's what was throwing me off because I was thinking.
Oh, gotcha. And you know what? Maybe I mixed it up and said it the backwards way. And if I did, I apologize. But is that better? Is that okay now?
Yeah.
How are we doing? Are we okay? Questions, issues, concerns? Okay. This whatever the problem on the test that looked something like this tripped up a lot of people, which is why I assigned it on this homework and why I wanted to go through it, so that when you go back and do it on the test corrections, hopefully it's more attainable. And honestly, friends, if you're working on those test corrections and you need help, you let me know and I can help you with it, right? Like, I'm not going to just leave you there to flail.
What is that?
Figure it out. I'm telling you how my break was. Gotta read it.
What?
What?
Wait, isn't -1i?
It is.
Oh, I ate a lot.
Sigma. Pi.
What does sigma mean?
Some
The sum.
pie, and it was delicious.
There you go. Good work, guys. Oh yeah.
What pie did you eat?
I had some pumpkin
That's
pie.
good. And strawberry rhubarb is good.
Ooh, I like strawberry. I didn't have any of that.
That's because rhubarb's out of season.
It's true. That's usually like a summer deal for our
And
family.
cinnamon. Or no, wait, not cinnamon pie. Oatmeal pie with cinnamon ice cream is so good.
See, I just like chocolate.
I think we should all go to her house for ice cream and pie. All right. Let's talk Newton's third law, ladies and gentlemen. Let's get our brains back in this. Yesterday,
I'm in the pie mode now.
I'm sorry, we're going to get into the Russian ice dancer mode.
Oh.
Yes.
Oh, yes.
Wait, are you ever?
I'm always in Russian ice dancer mode, guys. It's great. All right.
I'm
So
watching Ice
I know, right? Did you say ice fishing or ice dancing? Ice dancing?
Dancing.
It's gonna be
I'm not
great.
watching Ice
You guys are going to be glued to the,
Dancing.
I don't know, a couple of weeks, I think.
And no, and look at
All
the
right.
Olympics. Oh no.
Look at how wet it goes.
I just want to make sure we get through this stuff so that you know how to do stuff for, the days beyond today. Okay. So yesterday we told a story. Then I just want to recount and make sure it makes sense to you. Told a story of my least favorite Winter Olympic sport. Okay. Alice and Boris, the Russian ice dancers, right? The reason I think that it's terrible is because it's really sappy and goofy at the beginning.
And
They
they don't jump.
don't jump. They don't throw each other. There's no risk factors,
And they
right?
gaze through each other's eyes and it's weird.
It's gross, right? But so they start like this with their hands like this. They're gazing into each other's eyes. The music starts, and this is where the physics happens, right? The music starts, and what happens?
Push each other.
They push. Okay? The push is the important part. Now, I didn't hammer this home yesterday, so I want to hammer it home today. How many objects are required for any force to happen? 2. Not even at least, because I always wanted to say that, right? At least. But it isn't. It's always exactly 2. Yes. So let's write that down because that's important. For any force, making me unhappy. To occur, 2 objects are required. Do you remember at the beginning of this whole forces business when I was being really, really cranky about making sure that you labeled things? The force of the earth on the frog, the force of the table on the frog, the force of the water bottle on the, like whatever it was. It's always how many objects? two. It's a relationship between two objects. Super important, friends. Okay. So we have Alice and we have Boris, and they're pushing on each other. What happens to Alice? She goes flying, right? What happens to Boris? Right? Then the question that I put to you was, who pushes harder? Alice or Boris? Your gut feeling probably isn't the right answer, right? Gut feeling might be that Alice pushes harder because Boris is enormous and she gets him to move, or that Boris pushes harder because Alice flies down the road, right? Or flies down the ice. What are you observing when you watch them do that? Are you observing the force, or what are you observing? You are, and what is that? What is it that you're observing? She starts at a velocity of 0 and she ends up at a velocity of something. So you're observing an acceleration, right? Yeah, so let's write that down too, okay? So when a force is applied, we observe the result. Seriously, this is ridiculous. And the result of a force being applied is the acceleration. Alice goes flying. She has a really high acceleration. Boris goes because he has a low acceleration. But the reason that their accelerations are different is not because the force is different. It's because the what is different. The mass is different. Yes. Yes. So we have, oh, go ahead.
Alright, so if we said weight instead of mass, is it still considered correct?
So it's not incorrect, but it's less,
Correct.
it's less palatable. Like it's less,
Minimally correct.
She doesn't want us to
it's
sound
not
dumb.
wrong, but it's not,
Grab credit.
does that make sense?
Yeah.
Because as mass goes up, weight goes up, but it's the mass that we really care about. Does that make sense?
Yeah.
Okay. Yeah. It's a very, very fair question, and I'm glad you asked. Yeah. So the acceleration of, oops, I'm going to write that as a nice little A, of Alice is equal to the net force, or the force of Boris on Alice, divided by the mass of Alice. Okay? The acceleration of Boris is equal to the force of Alice on Boris divided by the mass of Boris. Indeed.
Oh,
Yeah. This acceleration is enormous. I'm just trying to show you in like physical like size, just so you can see it. The forces are the same. Are you with me there? You can have a large number and a small number, and they can result in the same force. How are we doing? Are we okay? Did I mess you up with your pretty pens? I'm sorry. One could also write it like this.
Oh, I just messed it up too. I said Boris and
Oh, sillies.
is that how you talk to your kids?
No, I try to avoid talking.
Oh man, I just did it again.
Did anybody get them some extra whiteout for Christmas? I don't know.
Well, I had white out, but somehow it disappeared.
Oh, the Grinch came and got it or something. I don't know. Watch out. So the key here, ladies and
Now you mean
gentlemen,
the mass is supposed to be big here.
the one that's big. Boris's mass is enormous. Okay, besides our writing down issues that are going on here, how are we doing? Are we okay?
Yes.
Okay. So the forces are how do they compare?
Look how ugly this looks. There's a big
That's
purple
pretty
dot.
embarrassing. Man, that's not going in like any sort of like fancy.
I mean, your notes still look better than mine.
Mine is like great, because look at mine.
I do
Mine's
have a big.
perfect.
Those are perfect. Those are like, yeah.
You know, like
All right.
med school.
Yes, John.
Would it look the same? The mass is different and the accelerations? Oh, different?
Are different as well. Yes. Does that make sense?
Yeah.
Do you want me to say, like, is that sitting okay in your brain? No? Which part, can I ask? The whole darn thing? Okay, okay. I'm gonna write it down a different way. I don't know if this is gonna help or not, but are you with me here? Okay, so, here, I'm gonna go back to my pictures from yesterday. Oh, so don't listen. I mean, I don't mean that literally, but, so this is a picture I do yesterday. Okay, we did this over time, but here's the thing. This little rectangle,
Yeah, go get the skateboard.
I'll go on it.
hold on a second, let me talk here. This rectangle is Alice, okay? She's got some forces acting on her. Are you with me there? She's got Boris pushing on her. Things are go that way. The earth pulls on her, and the ice pulls on her, or pushes on her. So far, so good? Okay. This is Boris, the blue one, okay? Alice pushes on Boris. The ice pushes on Boris. The earth pulls on Boris. Life is okay? Okay. So they stand there. And they're gonna push apart. Have you ever watched ice skating or ice dancing before? Or tried this with anybody? No? Okay, we're gonna do it. Wait. Who's gonna be my partner? Me? Who said me?
Tatum.
All right, Tatum. Woo! Well, first time for everything. All right, I'm not very good at it. I don't really trust myself, but we'll do our best. All right, can you see us over here? You can come over. So Tatum is going to be Boris, not because she's ginormous, but because she has more mass than I do, because I'm not very large at all. I'm not even 5 feet tall. Do you guys know that? All right, so we're going to stand here. We're doing this on this because we don't have ice. Ice gets rid of the friction, right? So here we are. We're going to gaze at each other. So we're going to push. Whoa, like this. Are you with me there? Okay, so there I go. I'm free. And Tatum's going. Yeah, I mean, it's not super easy because like our masses probably aren't very, very different. Are you with me there? Okay, but the question is who pushes harder, right? The truth, and this is the thing, this is the most important part, is that we push the same amount. The forces are the same. The thing that's different is not the force, it's the what? The mass. And as a result, the what, guys? Acceleration. Yeah. Up, down. All right. We want to make sure this really makes sense to you. We're going to do this right now. I'm going to do this right now.
Oh, I was gonna ask you a question.
Oh, how's that going?
It's like, maybe we're gonna use it for the homework.
What?
It's like,
Well, don't, just hold on a second. Just hold on a second. Wait a second.
What was about the homework? Yeah, I heard about pulling the rope.
Yeah, we're going to do it right now.
That's what I was asking.
Yeah, I'm going to see if you guys can
Yeah.
triple up and figure it out. All right, so I want you to be careful with my spring scales so you don't break them. So stop. Just stop for a moment, okay? There are two sides to the spring scale. There's a side that measures mass, there's a side that measures force. The mass is actually just calibrated so that it works on Earth. Wouldn't work on the moon if you did wrong reading. We want to look on the side that has the new, that's measuring the force, okay? So what you're gonna do is you're going to hook them up with a partner. And really so the goal is twofold. One is to see if you, once they're hooked together, can apply a force without your partner applying. So see if that's possible. Yes, hook them together, and then you each are holding one, and then see if your partner can apply a force without you applying a force. And then, it's not, and then measure the forces and see how they compare.
They're always gonna be equal because whenever I pull it pulls.
Oh, that's more right there. So if you pull it all the way around, you'll be able to see it. So pull it just a little ways and measure it. Okay, see how it goes. Measure the forces. What's going on?
Nothing was good.
Or just pull that.
I thought she was, I was you try to do it. You can't work.
Or it can work. Yeah, so don't, if you pull it all the way, it's not gonna work well. If you pull it apart,
because
it's gonna measure the force.
Yeah, that's not a word.
You're pulling three. Whoa. If you pull 4, he pulls a 4.
Dang.
Whoa. If you pull just 1 Newton, what does your partner pull? 1 Newton. 2 Newtons, 2 Newtons, 3 Newtons, 3 Newtons. Is it possible for the forces to be different. If you have working spring scales.
I think the spring scales, they're like, it doesn't work, but the spring scales will hold. But I don't know how to do it.
Yes, in that case, it will work. Okay, does that make more sense? Okay. All right, so stay with me, ladies and gentlemen. So this is pulling. Pushing does the same thing. Anytime you apply a force, one object on another object, the interaction is going to result in forces that are the same magnitude. Magnitude means
Like size.
size, quantity, absolute value, not direction. Tell me about the directions of the forces. If Abdul's pulling this way, and Dylan's pulling, and Dylan's pulling, which way are you pulling? What happens? They go in the opposite directions, right? I'm going to ask other couple questions that are important to know. Who pulls first, Dylan or Abdul?
Neither. Same.
Same time. Who pulls for longer?
The same.
Same. Are you with me here? Same.
Exactly.
What's that?
Same.
Who's the same? Who's same? Okay. Are we doing okay? We're still happy? Okay. I want to do this activity right now. So what I need you to do, I need you to put the, when I have you get up, I want you to put the spring scales back, okay? And you are going to divide yourselves up. I'm going to divide you up into 3 groups, and I'm going to put each group at a different back table, okay? Once I do that, I'm going to give you some instructions, and I need you to listen and follow those instructions very carefully, okay? So we're going to number off by 3s, and we're going to start with Haley. So go ahead.
2, 3,
Nope. Number off by 3s. Always happens.
3. I was like, what number am I?
Dude, wait, hold on.
Wait, hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay.
What do you mean?
2, so we have to number off by 2.
No, we're numbering off by 3s. It's fine. I just thought we might have perfect numbers, but it's all good. 3.
1.
Okay, sweet. So again, put the spring scales back. Group 1 is going to go over to that table. Group 2 is going to go to here, and group 3 is going to go over there. You don't need to take anything except your body. Use your brain.
This will be my brain.
Yeah, you kidding?
Yeah, you
Me.
All right. 1. Awesome. All right. I gave you some pieces of paper. Listen carefully, please. On those pieces of paper, you can flip them over and take a look at them. I want you to find the force pairs. I want you to find the force pairs. The forces that go together.
Force of volleyball on volleyball.
I mean, say hi.
Mine probably the other.
So there's force of bowling ball on the first. Then why is there an asterisk on it? Is there an asterisk on it?
Don't worry about the asterisk yet.
Oh.
That's for something that's coming up.
Force of bowling on force of volleyball or wait, why is there force of volleyball?
This one,
Like that's why the third.
All right, let me pause you for just a moment. I want everybody's eyes up here, everybody's mouths quiet. Just listen. I've not used the term before, but I wanted to see how we were doing with it. What is a force pair? A pair of forces, right? Forces always have to come in pairs. The force of Alice on Boris, what's the force pair that goes with that?
Force of Boris on Alice.
Boris on Alice, right? Are you with me there? Okay. So if you have not yet paired up your pairs, do that now. okay? Then we're gonna read them out loud, and I want you to listen carefully when we read them out loud. So, you all, I think you'll have 3 pairs, right?
Yeah, we have to.
Okay, so except for this group, everybody's gonna take one of those pairs. So, just like, so Dylan's gonna take a pair, Tatum's gonna take a pair, right? Okay, and we're gonna just,
Wait, both of us.
oh, I'm sorry, so just take, so everybody take one, and then somebody will be not speaking out loud. So, guys, I need you to listen. This is a listening activity, and I really want this to get in your brain, because if you don't, you're not gonna retain it. If you listen carefully, this will work, okay? So Dylan's gonna start, he's gonna read his 2 forces really loudly so that we can all hear them, okay? I want you to listen and make sure it sounds like a pair to you. And I want you to think about and imagine what that looks like. Go ahead.
Force of bug on earth. Force of earth on bug.
Keep going. Keep going.
Force
Listen.
of bug on car. Force of car on bug. Force of car on road. Force of road on car.
Go.
Force of bowling ball on bowling pin. Force of bowling pin on bowling ball.
Force of bowling pin on lane and force of lane on bowling pin.
Okay, so we got, force of bowling ball on earth, but then we got the same one.
Oh, did it not get flipped? Sorry. So,
Yeah,
so do it right. Yeah.
It's supposed to be force of earth on bowling ball instead.
Force of table on earth and force of earth on table.
Force of earth on frog and force of frog on earth.
Okay.
Force of frog on table and force of table on frog.
Do you hear how that sounds?
Yeah.
All of those force pairs are just 2 objects that you say force of, and then you just flip the objects. You with me there? Okay, that is what a force pair is. My next task for you, with the pair that you are working on, and those of you that don't have a pair, you need to help out somebody, okay? I want you to determine which of those forces is larger. Go.
Honestly, it has to be.
No.
Might be.
Well, like, which one is?
Oh, yeah.
Which force is larger?
I'm not the people.
Because the bowling balls are coming through the ground. The bowling balls.
No, wait, what are we?
The normal force.
No, I'm gonna use the
The car would be using less.
Which force?
Just turn it on the, right?
Oh, yeah, you're right. The force is moving that. No,
Not exactly, but like we don't exactly.
But,
And be like,
you're right, so then it has to.
Just
go
because,
Wouldn't this be the largest, because it's top one is the bowling.
But that's where it's like,
Right at the moment of impact.
So you don't need to write anything down yet. You don't need to write anything down yet. Please don't waste my markers.
That's what
Please don't
we
waste my
determined.
markers. Don't write anything down yet. That's not what that's for.
No,
Please
but
erase that. Thank you.
it may be saying.
All right.
because horses go higher where Alice goes way far. It's like the bowling ball.
You know, I get what you're
Who had
saying.
the bug? Are you guys the bug people? All right.
Which force is bigger?
Haley, what did you guys figure out over there?
No, the force is.
They'll be the
Okay.
same.
Say again.
They'll be the same.
Thanks, Haley. Tell me, Haley, what did you learn?
Sorry.
So that they'd be the same.
They'd be the same. Which 2 forces did you have?
The force of the frog on table and force of the one frog.
Force of the frog on the table, force of the table on the frog. That seems reasonable. The frog's not going anywhere, right? Is that why they're the same?
Well, so it's just like, we discovered it yesterday, but it's the same always. There's a force and a pair, and it's always the same.
So does it matter if the frog is moving or not?
No.
It doesn't. Let's see, Maggie, what did you guys have? What was your force pair?
A force of a bowling pin on a lane.
Okay,
So it would be the same.
as the force of the,
Force laying on the wall.
hold on, no. Wait. Tell me one of your forces again. I just want to make sure I
Force of
understand.
a bowling pin on the lane,
Okay. And how does that compare with the other one?
it would be the same force as the lane on the board.
The lane on the bowling pin. So the pin is pushing which way on the lane?
Wait, down.
No,
Down,
lane.
and the lane is pushing up.
The pin is, and I want you guys to listen, it's not just because I'm just talking to Audra, right? You're all trying to make sure you understand this. Because sometimes she doesn't answer the questions right. Most of the time she does. But I want to make sure that you're listening and paying attention, right? Okay? The pin is pushing which way on the lane? The lane is pushing which way on the pin? Up. Are we with me there?
So we're talking about the X, or the Y direction, not the X direction.
In that case, yeah, because the pin is just sitting on the lane. Yeah, yeah. Okay, which one did you have, Janelle?
I had the car and road.
Car and road. So the car pushes which way on the road? And the road pushes which way on the car? Okay. And Dylan, which one did you have?
Force of the earth on the bug.
Okay, I didn't want that one. Which one did you have?
Forcing farm bug.
Car on the bug. So we have a bug flying this way, we have a car going this way. How many of you have been in a car with a bug flying towards it ever? Okay, it goes splat, yes. My friend Ben would be so proud of you. He loves saying splat, yes. So here we go, we've got a car coming this way and a bug going this way. Does the car apply a force to the bug?
Yes.
Yes. Does the bug apply a force to the car?
Yes.
How do the forces compare?
Aren't they always equal? Equal to opposite.
But do you want it to be?
In your head, no, but in
Physics.
physics, yes.
In physics, yes. Why in your head, no?
It just doesn't seem like something so little compared to something so big would have the same amount of force.
The same amount of force, but what is it that we see? Do we see the force?
No,
No.
you see the
No.
acceleration.
We see the acceleration, and does the bug accelerate?
Yeah.
Hot diggity, it does, right? It's going this way, now it's going that way. Are you with me there? Absolutely, the bug accelerates. Does the car accelerate?
Little bit. Like, almost
Theoretically.
very, very small.
Not even theoretically, like it does, but it is not a very big amount. Are you with me?
It's like
It's so small because the mass of the bug is
so small.
so small. But if you imagine the same thing, instead of a bug, you have two cars coming at each other, right?
Yes.
Then they absolutely both are going to accelerate in a noticeable amount. When you're driving your car, as the bugs come at you on a sunny, nighttime, warm summer evening, the bugs are going. It's not like when you're driving, you're like shaking, right? The car doesn't react that much because the bugs are very, very small. With me there? But absolutely, your car is accelerating. Not by much, but by a little bit, yeah.
Maybe this is a bad example, and maybe because it's kind of gross, but
It's
when you're
okay.
on like a jet ski and it's really like buggy out and you're like going so fast the bugs like hit you
Yeah,
and they hit
disgusting,
you
but yeah.
hard and then you kind of like,
Yeah.
I don't even think it's because they hit you so I think
Kind of a surprise, probably more of a and I'm gonna use the word reaction, but it's because it's a biological thing, right? Because you are like actually like your body is having some sort of like, oh, that's disgusting kind of reaction, not a reaction, right? Yes, yes. Yeah, there are appropriate times to use that word. Newton's third law is not one of them.
I think you forgot the whole
I know, right? Okay, so Abdul noticed that there was one object in his pair that had an asterisk next to it.
Yeah.
Everybody should be able to find an asterisk next to their one object. On your whiteboards, I want you to draw, and I need you to listen carefully so you know what you're doing. I want you to draw a free body diagram of that object. Okay, go. Draw a free body diagram of that object.
And then you gotta draw a pin. That's not a circle, that's a pin. And you draw a circle. Yeah, that's
She didn't say anything about the other option. So maybe just.
What is a free body diagram, you guys? Okay, guys, listen, can I have your attention for just a second? So my question was, what is a free body diagram? And Promise, what did you say?
Like when an object, when you show the force that the object applies on, like, the surface and other things. And when, like, you also show the forces that the surface is applying, is exerting on the object, and vice versa.
You're on the right track, but I think you're trying too much. How many objects are in a free body diagram? We've been drawing free body diagrams for the last like month and a half. How many objects? One. Sometimes you like draw the surface, just not get confused, but it's one object and what? The force is acting on it. Make sure you've done that. And this is where I really want you to pay attention and write out those forces correctly. FG isn't a thing, friends. FN isn't a thing. Force of the omelette. Force of the omelette, right? It's gotta be something on something. Every time.
Force of earth, water, force of bowling, then the force of the.
It's good, Rob.
Just say pin.
Ooh.
Riley?
This one's Rob.
She already voted out.
Riley,
Like,
Riley is my dog. He's 13 years old and very sick.
Harley, I'm sorry. I don't know why I called you Riley.
You guys can figure it out. Use your brains.
Then what else? There's a force of a bowling ball.
I guess
It's not a bad question to be asking. How are we doing over here?
And then the bowling balls are gonna go from our side. Like the arrow.
I thought he's flying.
And then the opposite, so it would be the force of the bowling ball.
I'm asking.
That right there.
Because I know the answer, but I want you to figure out the answer.
That's what I was debating.
Forces, one object, and the forces that act on the one object.
Force that way. Versus the bowling ball.
You mean this way, where are you trying to? This is force of bowling ball on bowling pin. We're assuming the bowling ball's coming from here in the arrow.
One thing that you might want to think
Yeah,
about
you
as you're
can
trying to
try it.
figure this out
No, you already did it, right? You already did it.
is the net
No,
force
you still
gonna
need-
be
you still need-
zero?
I'm saying like the, because the pin's gonna push back on it. So this is the pin pushing back on the bowling ball, assuming the bowling ball's coming back. Pin on. Okay.
Alright, yeah. Jeez.
Like, I was being the one who's saying bowling ball.
That's a big guess.
You got it. Are we taking it?
A to the J of the circle.
What about friction? I didn't even. I got it too.
There is no friction on bowling, like bowling lanes.
There's always
No, on the
friction.
pin there.
Can you do the first break it like that?
There is not, it's a constant.
Alright.
Then the world would be better.
Otherwise stated. Yeah.
What about air resistance? What else can it be?
It's having some problem. It's like this, you're like.
You see what I'm getting at?
Alright, here we go. Ladies and gentlemen, it's almost time. I need your attention up here so you can take a look. I want you to listen carefully. I want you to think this through. I will tell you that this is one of those, like, we have to crack your brains and make sure that you really get it, because I'm telling you lots of different stuff here. This is not hard stuff, but it's not intuitive. Are you with me there? Okay? Every force requires two objects. Every force has a pair, A on B, B on A. You with me there? Hold on, wait for just a second, okay? The free body diagram we'll go through tomorrow, but I just want you to keep in your head one object, the forces on that one object. Okay? Hold on to that, we'll do it tomorrow. Because that bell is ringing at crazy times again. Woo!